the right hand. Here's how this game works. The other thing which angular momentum has in common with linear momentum is not only is it conserved, it is also a vector. I know, that is a vector. It has direction. Here's how it has direction. The right hand is the right hand. Take the fingers on your right hand and curl them in the direction the object is rotating.
Oh, we did this.
This is called a right hand rule. And your thumb, that's sticking out to the side, points in the direction of the momentum vector. It also points in the direction of the angular velocity vector.
Wait, what?
So, wait, here we go. We're going to unconfuse you, Brandon, okay, with an example. So, listen carefully. Usually I say your choices are up, down, right, or left. However, now this is three-dimensional. Your choices are up, down, right, left, towards the back of the room or towards the front of the room. So, here's the question. What direction does the angular momentum vector of the wheel point right now?
I feel like this way.
Clockwise.
Decide on an answer.
How do we do the right hand rule again?
Curl the fingers on your right hand in the direction the object is rotating. So here we go. Right hand, you ready? Curl the fingers in the direction the object is rotating, which is this way, and my thumb points towards the board.
The board.
So the angular momentum and angular velocity vectors, because angular velocity is also a vector, point towards the board. Rotating this way,
What is that?
the angular momentum vector now points towards the back of the room.
Wait, why wouldn't the angular momentum and angular velocity vectors be like, I don't know, in my head it would make more sense if they were like tangent to the rotating object.
Sorry, no. Okay? In addition, because the math won't work, Brandon,
Oh.
that's why. In addition to that, torque. What's torque equal to?
RF something.
There we go, RF sine theta. Only I'm going to get rid of the sine theta, and we write it as R cross F, which is R crossed into F. Right hand rule. Point your fingers in the direction of the R vector so that they can bend without breaking all your knuckles in the direction the force vector points. So, I'm going to put my origin at 0, and I'm going to push up at the 70 centimeter point. Good? So, fingers point from the origin to the application point of the force, because that's the direction of the R vectors, they point that way. And then they need to be able to curl in the direction of the force, but the force is pointing up, and if my hand points this way, I have to break all my knuckles to get them to point in the right direction. So to get my fingers to curl in the direction of the force, since I'm pushing up, I have to flip my hand over so my torque vector points towards the windows. Which means this torque, pushing up here, will cause a change in the angular momentum, pointing towards the windows.
I'm not understanding this one.
R cross F,
Yeah.
Yeah.
fingers point in the direction of R, which goes from the origin to where the force is being applied.
Right.
So from here,
Mm-hmm.
so they're going to point this way,
Right.
okay? Now you need your hand oriented so that your fingers can bend in the direction the force vector is being applied.
Oh.
Okay? Right now, my hand's not oriented that way.
But you have to go like
Because
that.
I would have to, snap all my knuckles to get it to point in the right direction. So I've got to flip my hand over, which changes the direction my thumb is
And
pointing.
you're still pointing in the direction of the.
Okay? Everybody good? Now, just to make this clearer for Brandon and everybody else, hopefully, I'm quite certain Brandon will catch on to this. Brandon,
Yes.
Cartesian coordinate system.
What about it?
You ready?
Sure.
Good. Positive y, negative y.
Yep.
Positive x, negative x.
That's how it works.
We're not done. positive z, negative z.
Yeah, three-dimensional Cartesian coordinate system.
Three-dimensional Cartesian coordinate system. Origin is here, my force is out here. My r vector points to the,
Positive x.
it's positive. My force vector I was just using pushes
Positive y.
up, it's positive. A positive times a positive is a
Positive.
positive, and the resulting torque vector points on the positive z-axis.
Oh, that's cool. Okay.
If I push in the opposite direction, my torque vector will point on the negative z-axis. And you can figure the torque values and add them tip to tail, just like any other vector, to determine the resulting torque vector and its direction in 3 dimensions. Happily, we will not do that last part. Okay? But
I blanked
the
out.
Cartesian coordinate system, Brandon,
Mhm.
is a right-handed system because of that. Okay? Note, torque is R cross F, not F cross R. F cross R is the opposite of R cross F, because on a cross product, you point your fingers in the direction of the first variable, and they have to curl in the direction of the second variable. So we write it as R cross F.
So why doesn't it work with your left hand?
Because the Cartesian coordinate system is right-handed. If you try it with your left hand, point my fingers in the direction of the R vector, rotate my hand so they can curl in the direction of the force, and my thumb points on the negative z-axis. Our Cartesian coordinate system is right-handed, not left-handed. Okay, so you need a Cartesian coordinate system where you reverse it. Get that game to work. All right, that having been said, running out of time.
Math is dumb.
Now for some fun.
Unicycle?
So, we're going to start with this, okay? If I have my wheel rotating this direction, we've already said that the angular momentum vector and the angular velocity vectors point towards the wall, right?
Yeah.
The board. There is no right now vertical angular momentum vector, right? Everybody okay? Everybody good with that? But if I were to rotate this up this way, there would then be an angular momentum vector for the wheel pointing
Down.
down. Everybody okay?
Right.
But
Yeah.
angular momentum is
It's
conserved.
spinning this way.
You ready? I am definitely going to do magic.
I'm scared now.
Are you
I'm going to use my Jedi mind skills. You ready?
He's gonna marry
There's
Poppins.
no vertical angular momentum vector, right?
Yeah.
But if I point the wheel up, then there would be a vertical angular momentum vector for the wheel pointing down.
Yeah.
Which means I would need to rotate in a
When did he
direction.
start
Hello?
spinning? When did he start
Right,
spinning?
Produce an angular momentum vector pointing
Oh,
up.
that's
Wait.
Oh my gosh!
Wait. My angular momentum vector when I did that, mine pointed up, the wheel's vector pointed down, the total vertical angular momentum was 0. On the other hand, if I point the wheel down,
I was just about to ask.
Hey!
You know, if we were in 1862, I'd throw you in the Salem witch trial.
yes, if we were in the 1600s, I'd get burned at the stake for that. Everybody good? And note, to change the direction the wheel is pointing requires a torque. This isn't an easy thing. A really fun thing to do is to get a gyroscope and wind it up so it's spinning really fast, put it in a box and hand it to somebody and tell them to take it somewhere. Because wherever direction you try to turn it, it pushes back the other way.
Aren't there a bunch of gyroscopes in phones?
Yes, there are also gyroscopes though in submarines. That's even more fun. So let's see here. Brandon, hold the wheel. Both hands. So I'm gonna spin this
It's heavier than you would.
this direction. So it's gonna have an angular momentum vector pointing towards the back of the room. Everybody okay? All right. And right now, so once I get it spinning, great. Point it at Ted. Good, now point it over at David.
Oh God.
Oh god, I swear to God.
It's really hard to turn it.
Yeah, it wants to point down whenever I go to the left, and wants to point up whenever I go to the. Jesus, right.
Right, okay. Now stop it with your table, because I'm not grabbing it. Okay.
Oh my god.
Oh no.
Oh my
Bruh.
god.
Why'd
You do like that?
Everybody okay? We got it? All right, so there's evidence that the angular momentum is a vector. We can also do this. Great Jedi mind trick.
I've never really understood why it would be a vector in the other direction, but now.
Now you kind of do, huh? You don't need that much. We ready?
Is this similar to how helicopters work?
Levitation.
Oh,
Always
no.
fine.
Oh god.
You're not.
Wait.
Oh!
This is magic. He's a witch.
The combination of the two forces that are acting here. One force is there's a torque exerted because of me pulling up and weight pulling down, which normally would cause the whole thing to rotate down, right?
Yeah.
Except that would change its angular momentum vector drastically, wouldn't it? Okay, the combination of that torque and the torque produced by the friction between the peg here and the bearings in here and the rest of the wheel produces a total torque which causes the whole thing to rotate this way.
That is so weird. Wait, is this practically applied anywhere in the like? Or
Yeah.
Where is this practically
The
applied?
spinning thing, because it maintains its direction,
Uh huh.
that's what we use for gyroscopes in submarines because they're underwater. Tell what direction they're pointing.
Oh.
You spin the gyroscope up to speed and you get it pointed north, and you set it in an oil bath that it just floats in. So when the outside container turns, it just sits in the oil bath and it maintains the same pointing.
Oh.
Yeah. So that's how.
Yeah. Is this something?
Now
is this something in a
helicopters,
helicopter
the
now?
blades have a definite angular momentum. So the rotor on the back produces a force to push the helicopter, so that when the blades spin, the helicopter doesn't spin the other way.
Yeah, because whenever you shoot up,
Okay.
whenever it's
Speaking
the
of which,
backpack
Amy,
blows
close
up,
your
that's what
backpack.
spins out.
Jason's backpack is closed. Good. Amy's backpack, yeah, where's your backpack?
Like they can fly with just the
You'll see.
rotors on top, but they-
I'm stealing your stuff. Never mind, we're not using your backpack. Oh, good, now I have two backpacks. I need a volunteer. Okay, Adrian just volunteered. Okay, so the backpacks represent essentially point masses. Step back just a little bit. Okay. All right, everybody good? The backpacks represent point masses. Okay, so we're going to start like this, with the backpack sticking out. And Amy, give one of the backpacks a little bit of a push so I start, not Amy, Adrian. Give that a push so I start rotating. Good. Everybody all right?
Yeah, that makes sense. Oh my God! That's how ice skaters in the Olympics. That's how they spin faster, by bringing in all their mass into one point.
Thank you, guys. So, here's the thing. Backpacks essentially represent point masses. We're just going to ignore the fact that the radius of my arms was changing. I think my arm got it. But notice what's happening. The MR squared value is changing. The mass of the backpack stays constant, but the R values are decreasing rapidly. When the R value goes down, rotational inertia goes down, but the angular momentum is still a conserved quantity.
So it has to go up.
So what has to go up?
The omega value.
The omega value, the angular velocity goes up to compensate for the decrease in the rotational inertia.
So that's why. Oh my God, it makes sense because that omega r squared value has to stay the same. So if your radii value is getting smaller, that means the omega value has to go up, and vice versa. If your omega value goes down, that means the radii is getting larger.
Yes. This goes for ice skaters. It goes for gymnasts. Swinging on a bar. They swing down to the bottom. You want to get back to the top. You have to speed yourself up. So you shorten your radius by bending at the waist a little bit. And that speeds you up and you come right back to the top. Straighten it out. Fall straight. Shorten your radius to the bottom. Speed up.
Divers.
You can make it back over the top.
Same thing with divers.
Okay? Same thing with divers. You want to flip fast